Okay, well, thank you all for coming today. Thank you, Kevin, and thank you, Bids, for allowing me to tell this story. And of course, I'd like to begin by acknowledging my co-authors, Alain Dax and Nishant Desai. We've been working on this project, I think since most of spring semester in 2017 and through the summer. And the title, as you see, do Steph Curry and Klay Thompson have hot hands? So maybe I should ask who is a basketball fan here, or who knows who these people are? Okay, well, not most of you. So I'll say a little bit about who they are. These guys are star basketball players for the Golden State Warriors. The Golden State Warriors are a dream team. Locally, they're based in Oakland at the moment. And they won the NBA championship in June, I guess. But they've been winning championships. They've been on top of the league for a few years. And these particular players are very, very popular. So we picked on them, although we'll be looking at more basketball players besides these guys as we go through the talk. So one theme here is basketball. There are two other themes, statistics, which touches pretty much everything I do, and also human error, I would say, is maybe even the dominant theme, even more than basketball. So has anybody heard of the psychologists Daniel Kahneman and Amos Tversky? We were talking about him at lunch, so it's smaller than the number of people who know about the Warriors, although they may be just as famous. They were written up, there's a book about them by Michael Lewis. Maybe you've heard of him. He's a pretty famous author. He wrote a 2016 bestseller about their relationship, which is a great place to learn about what they did. And I will tell you a little bit about their work today. But they're kind of like connoisseurs of how people make mistakes, human error, which sounds a little dismal, but actually it's kind of charming also. So fits in. So that's those three areas will be woven together. And just as an aside, as Kevin mentioned, I work in financial economics, both academically and practically at Aperio Group. And everything that I'm going to say about basketball has a parallel in terms of how financial markets work and how people make decisions about their own money. And I'll touch on that maybe a little bit, but it's really amazing how close the subjects are. So here are the topics. Hot hand in basketball, I'll say what it is. Talk about a small sample bias. We'll talk about measuring how hot hands are in a finite setting with data 8 type techniques. I'm hoping most people know about data 8, even if you don't know about the Warriors or Kahneman and Tversky. Data 8 is an undergraduate course here at Berkeley in data science. It's becoming very popular. Here's the title of the talk again. We'll look at a particular example. One of our guys, Klay Thompson, actually scored 60 points in a single game last December. That's a lot of points, even for a superstar. And we'll look at that game and then summarize. So the hot hand in basketball. Now this is an old idea. I think I learned it 50 years ago from my father. So I grew up watching basketball. We were watching the New York Knicks at the time. I grew up in New York, and if you don't know the Warriors, you probably don't know these guys either, but there was a dream team. Thank you. There was a dream team then too. The names of the players, Willis Reed, you might know that name if you like basketball. Dave DeBusschere, Earl Monroe, Senator Bill Bradley was on that team, and my personal favorite, Walt Frazier, who was the point guard. And these guys were amazing. And what would happen, they weren't all kind of on at the same time. They'd be playing basketball, and one of them would seem to get hot. One of them would start scoring a lot of baskets, and all the other players knew to pass to that teammate because it seemed that his probability of making the next shot was elevated when once he got going. And so some players were cold at any given time and some were hot. You always passed to the hot hand. So the hot hand is widely accepted in basketball and in some other sports, and people think in money management and maybe in academic publishing even, I don't know, you get on a hot streak. Pass to a player on a scoring streak to benefit from an elevated probability of a hit. That's the idea. So this is Oracle Arena up there. That's where the Warriors play, and next to it is a photograph of a sign that's out in front of Oracle Arena, Feed the Hot Hand, showing that the concept, even though I learned it 50 years ago, is alive and well today. It's perceived as good advertising. We drove by, this is a photo by Ken Ribbett, who's here in the front row. I smiled when we drove by this sign the first time, not just because I'm so fond of the concept, but because of another thing that happened to me only 5 years ago. In 2012, I was reading this book, and it's called Thinking Fast and Slow. In fact, I was reviewing the book. And this is Daniel Kahneman's work. It's a popular book, but it's also a scholarly book. And it talks about he and his partner, who I mentioned, Amos Tversky, had understood and documented different forms of human error. And I started reading this and reviewing it because I wanted to learn about its applications in financial markets. I've been obsessed with the book ever since. But in this book, I learned about a study that was done in 1985 by 3 researchers. I hadn't known about I'd known the hot hand all my life. Here it is in 2012. I found out that in 1985, that the hot hand had been discredited as a concept by 3 researchers who showed it was a cognitive illusion. So data, it was a statistical study, it used data from the Philadelphia 76ers and the Boston Celtics. Those are professional teams, also from varsity teams at Cornell University. And the 3 authors of the study, their names are there. So Gilovich, Vallone, and Mr. Tversky, not with Kahneman on this one. Tversky was an avid basketball fan. He died, by the way, in 1996. So he is, fortunately and very sadly, no longer with us. But Tversky and his co-authors looked at data, asked the kind of question you would ask if you think that hands get hot, are there unusual streaks in this data? Or specifically what they did ask, well, they did a bunch of questions, but one of them is, given a certain streak of a given length, is there an elevated probability of making the next shot? Everybody at BIDS, I'm sure, working with statistical data, could imagine how an experiment like that might go. They found that no statistical significance. Tversky was a psychologist, worked with psychologist Kahneman. This fit into their long line of results that people perceive stuff wrong and that they continue to perceive stuff wrong even after they've been told what the right answer is. The result was very unexpected, and it launched a huge scholarly literature. So if you go to sports literature or other kinds of literature, there's lots and lots and lots of hot hand studies. So just want to say a little bit more about Kahneman and Tversky before I leave them for a while. The kind of nature of their results. We all know, well, we're scientists, right? So we make mistakes. Everybody makes mistakes. There's mistakes all day long. But what they found is a certain set of mistakes that we make predictably. And an example of that is to misassess the role of randomness in what we see. We're pattern seekers, right? We see 3 things. We think, wow, a trend, We just do this automatically. It's part of our nature. We can try and train ourselves out of doing that. But as interesting as the list of their mistakes is, these predictable, and you can be very smart, and you can be very educated, and you can be very disciplined, and you can be very determined not to make these mistakes, but you're going to make them anyway. They're just, you cannot learn not to do them. So that's Kahneman and Tversky. Tversky found evidence of his kind of thing. People misperceive randomness in basketball. Everyone was surprised. Scholars found it interesting, but the NBA didn't find it so interesting. So this is Coach Red Auerbach. This is, at the time, he was one of the most famous coaches in basketball, a subject matter expert, been massively successful, just shrugged his shoulders at the thing. So if this sets up like the kind of maybe climate that we have today, where you have the smarter than thou scientists, doing their analytics on one hand, and then other groups saying I have a lot of experience and I know better, and of course I should confess, I align with the scientists, and you think, wow, so cool, we're all seeing this, and yet it's not really there, and what do those basketball coaches know? So let me just explain a little bit about the framework of how the original experiment worked, because we're going to repeat it. The null hypothesis was pretty simple. It was that if you had a string of hits, say you shot 3 baskets, your probability of making the next basket was exactly the same as if you just made 3 misses. It's kind of like an independence thing. It just doesn't matter. That was their null hypothesis. They looked at different sequence lengths. They did a lot of variance on their experiment, but they did not find a statistically significant difference in the data, and they failed to reject their null hypothesis, just like good scientists. Okay, so that's all really great. As far as I was concerned, the subject was over, and I very proudly wrote about this. So Kahneman writes about this experiment in his book. He and Tversky were very tight, and his book is dedicated to Tversky, and wrote about much of the work Tversky did that Kahneman did not do. And so I kind of loved basketball and latched onto this in my review and had a big section on it. And if you take up Michael Lewis's book on Kahneman and Tversky, there's a big section on this hot hand paper. And Tversky is this great genius who understands the way in which people misperceive randomness. But 30 years after the paper, so now we're in 2015, 2 statisticians that I had never heard of, and I'll tell you about them, noticed that Tversky and Gilovich and Vallone had not properly set up their null hypothesis. So if you look in the literature, there's much discussion of this paper. There's countless references, but it's the usual thing. Well, look at a different team. Look at a different period. Look at a different sport. Frame hot hand in a different way than they did it, right? All the variants that we do as empirical investigators are in the literature. I'd never ever heard anybody accuse these guys of making a mistake. So I learned about this in a CDAR seminar from 2 students. These students were joint law and statistics, and they had just built a robotic judge, which was also, it's an aside, it was very cool. This is Ryan Kopis and Hannah LeCoeur. They've got great work too. And they mentioned in the course of their presentation that there was a mistake in this paper, which I loved and had written about, and obviously had not read all that carefully. So here are the guys who found the mistake, Josh Miller and Adam Sanjurjo. And what they show is something that I still find, well, I like explaining it. I guess I've gotten used to it. They show that in a finite sequence of independent coin flips, a continuation is less likely than a reversal. So this is like one of 2 content places. By the way, this talk is completely elementary. But this is one place where something, I think, kind of amazing happens. And so what I'm going to do is try and convince you. I mean, if you think of independent coin flips, what happens after something shouldn't depend on what happened before it. That's what independence means, or it's one of the things independence means. So this is a little bit disruptive at first. I think it's also true, and the subtlety of it was brought home to me by the number of hours I spent trying to convince Ken that this was actually a thing. So maybe it isn't completely elementary, but you tell me. I'm going to try and convince you now. And this is the simplest instance of the bias. It doesn't work for flipping a coin 2 times, but we're going to flip a fair coin 3 times. And I know that coins are not really random, right? They're physics, and I know they're not really unbiased, but But forgive me that, and pretend that I've got this coin that's actually, I can flip independently, and I have a 50% chance of getting a head and a 50% chance of getting a tail. Nothing else in the coin. And we're going to play a game. I'm going to be the flipper, and you're going to be the scribe. And when I flip the coin, two things might happen. It'll either come up tails or it'll come up heads. And if it comes up tails, you guys do nothing. And if it comes up heads, you keep that in your mind and write down what happens on the next flip. So this is kind of like the Tversky experiment. We're looking what happens after a hit, right? And this is an independent coin, so there should be no effect. So the question is, what is the expected fraction of heads in the recorded string? And what did Tversky and his co-authors assume in this context? Of course, that you would expect no effect, right? You would expect because it was all, the null hypothesis was independent. So here is what happens. You can see when you do only 3 flips, this same experiment can be done for any number of flips and also any length conditioning set. We can look what happens after 2 hits in a row. Right? So this is just the very simplest example. Length 3 sequences and only one element of my conditioning set. So if we had happened to have the sequence that come up first, 3 tails, you guys would not have written down anything because there were no heads for you to write something down after. And so that's kind of a problem, right? Finite samples are a problem. The second one is also a problem. You did get a head, but the head came at the end, so nothing happened after it. So we don't write anything down there either. So those are the 2 kinds of problems you have in the finite sample. Now, if it's tails, head, tails, you had head once, and after it came a tail. Then for heads, tails, tails, you had heads only once, and after it came a tail, and so on. And what I've got in the last column is the fraction of heads on your piece of paper. So given that you followed ahead, the expected value of seeing a head on the next flip is 0 and 0 and a half and 0 and 1 and 1, which is 2 and a half, and I had only 6 possible strings against which to take the average, and this is definitely less than a half. And this is the point that Adam Sanjurjo and Josh Miller noticed that Tversky had not noticed. It's a finite sample effect. It's a bias. So as the strings get longer, all else equal, if the conditioning set stays fixed, the bias goes away. And if we had an infinite data set, their null hypothesis would have been perfectly fine. But in a finite data set, as we see over and over, as we get to be better data scientists and less thinking about, oh, here's an asymptotic result, I'm going to apply that thing to my problem, we find more and more of these. So this one, I think, is especially nice. I will, it was, I think, a beautiful error. Is that clear to everybody? I mean, that's the whole point of the talk, is this mistake. So under the null hypothesis of identical independent coin flips, a reversal is actually more likely than a continuation in a finite data set. These guys, Gilovich and Vallone and Tversky, neglected this small sample effect. So how bad is it, right? Does it reverse their conclusion? So of course, Miller, Sanjurjo, they're very happy. They're writing lots and lots of papers. I mean, we all love to find these things, right? Especially in somebody's famous work. And there's a whole bunch of Miller and Sanjurjo papers. They're really great. They're full of estimates of the bias. Magnitude depends on the length of the conditioning set and the length of the sequence, and also on the fraction of hits as well. It can be substantial, even for a sequence of length 100, and certainly for sequences of length 20 or 30. These are sequences that we're going to be looking at, which is the number of shots that a great player might take in a typical game, or the number of shots that a team takes in a quarter. I want to talk about quarters in games. In the analysis that I'm going to show you, we look at players per game to get enough data, but we went down to looking at the team streaks per quarter where we had more data. I don't know about other basketball fans, but my experience is that someone might get hot for a quarter or half a quarter, but staying hot for a whole game, you don't see it. Players go in and out. So a quarter would be ideal, but we can't do it. We don't have enough data to do it with the, we don't have enough data to do it quarter by quarter for individual players, so we went longer. See, could matter. Miller and Sanjurjo, they revisited the Cornell study, the kind of least exciting part, if you will, of the original paper, and they found that the original finding was reversed in some examples. I have not been through their analysis of that, but I don't see any reason to doubt them. And I don't know exactly why they didn't look at the Celtic data and at the 76er data, but maybe it wasn't available. I mean, this is a real plug for now as we do more and more data science. We want to have researchers producing their data along with their write-up of the data. That certainly was not best practices in 1985. It may have just been impossible. There may not have been data available for these guys to look at the NBA study. But anyway, they seem to have found some reversals, so they say. So if you want to read about the sizes of the bias in all different settings, I recommend their paper to you. It's referenced at the end of these slides. But at this juncture, I'm going to go in a different direction and spare you learning a lot of inequalities and try and incorporate this small sample effect without having to estimate anything. So here's how we did it. We took one of our two players, that's Klay Thompson, versus Pistons. Pistons is a team, it's in Detroit, and the Warriors were playing the Pistons. And on, I guess it was December 13th last year, this was the string of Klay Thompson's hits and misses in that particular game. It's a shorter string than he usually takes more like 20 shots. He took 16 shots in this game, and this is the sequence. Now, if you were doing this experiment, I know that this is not a big basketball group, but you could split out free throws from 2-pointers, from 3-pointers. You could do a lot of things. We didn't do them. We took the full sequence of shots. It's a heterogeneous bunch of shots, but this is the string that you get. And this is the second point where there's something actually to think about. In this particular string, he made half the shots and he missed half the shots. So the statistic that I'm going to show you now is exactly the test statistic that was in the original hot hand paper. So we want to take the conditional probability of a hit given, say, 2 hits. We could have given 1 hit or 3 hits or 4 hits. And what I've highlighted up there, the colors aren't great, but the colors that are not black, I'm not even sure how to call them, are the places where there are instances of 2 hits in a row. And you see there are 2 right at the beginning. Those are overlapping. And then 1 in the middle and 1 at the end. So in the first case, after making 2, Thompson made his next shot. In the second case, after making 2, he missed his next shot. And then in the end case, of course, nothing happened because the game ended. He didn't make another shot. So it's this irregularity. You can see irregularities leading to the small sample bias. In this slide, I've highlighted not the conditioning set, but what came after. You see 2 zeros and a 1 highlighted, or the empirical probability that he hit given 2 hits was 1/3. That's part 1 of the calculation, and you want to compare that to the same calculation. What's the probability that he made a hit given 2 misses? So here I've highlighted all the instances of 2 misses in a row. There's a big cluster of them. And in 2 of the cases, the very first one and the very last one, there are 5 of them, he made a shot after missing twice. And in the other 3, he missed a shot after missing twice. So you get this calculation. The probability of a hit given 2 misses in this data set is 2/5. So we subtract. Our statistic, this test statistic, exactly the one that was used in the original paper, is the difference in the probability of a hit given 2 hits minus the probability of a hit given 2 misses. In the original experiment, the null hypothesis was that thing should be 0, but we know based on the small sample bias that actually the expectation is slightly less than 0 once we correct for that. So we've lowered the bar. It's now easier to find hot hands, and we can ask whether this negative 1/15 is exceptional or not exceptional. So now that we have data 8, that we have data science, we can look at all strings of length 16, half of which are 0 and half of which are 1. We can enumerate them. We can, oh, thank you. These are on the top, right. So we can compute the T2 statistic on every possible string. That's what we did. And here is the histogram. It's not the kind of histogram that used to get taught in statistics classes. It certainly doesn't look like a bell curve. A lot of our null hypotheses are not bell curves. Many of them are bimodal. When there's a relatively small string, it's very lumpy like this. But the critical region at a 5%, if you like 5% as your cutoff, is red here. Here's the observed statistic, which doesn't look very hot at all. So in this particular game against the Pistons, according to this analysis, Klay Thompson did not have a hot hand. So, of course, the other nice thing about, all right, so just to conclude, what happened to the small sample bias? Well, the small sample bias was, of course, baked in to the null hypothesis because we just worked with finite strings. And so the effect of a reversal being slightly more likely than a continuation is just in the data. This does not mean that modern data science can be used mindlessly to overcome small sample biases. But in this case, doing the knee-jerk thing happened to work. It was just automatically accounted for. So data methods kind of allowed us to very easily make a small sample, a null hypothesis of the correct size. Didn't need to use any asymptotics. Data science also allows us to run lots of examples. So in the 2016-2017 season, the Warriors played 82 games, and then they were in the playoffs. And they were supposed to win in 16 games, which would have meant a complete sweep, that no one ever beat them in the playoffs. But unfortunately, when they got into the absolute finals, the Cavs beat them in 1 game. So they actually took 1 loss. They're a really good team. But still, I think no one in history has ever swept the playoffs in the NBA. So we have 99 games. So Steph Curry played a total of 96 games. Thompson played 95. And we calculated this T2 statistic, what happened after 2 hits minus what happened after 2 misses, those conditional probabilities for each of these players in every game. And also, we looked for streak shooting in the team as a whole, so we didn't distinguish players. And then we can do quarter by quarter, as I mentioned, because we have enough shots by the team in a quarter to be able to do something maybe useful. So here are the games or quarters. This is your number of observations. These are the overall season percentage of these guys. If you are a basketball fan, you'll think those numbers are too high. They're high because the free throws are in there. Usually season percentage is calculated just on field goal shots, and sometimes even without the three-point shots. Well, everything's calculated these days. So these are higher than you'd expect because of the heterogeneity of the strings. And the average shots per game, Curry took 24, Thompson took 20, and the Warriors took an average of 28 shots in a quarter. Okay, so Splash Brothers. The Warriors, Steph Curry and Klay Thompson are called the Splash Brothers. You know, splash goes in. And they have, I think there's a Wikipedia page about Splash Brothers if you'd like to learn more about that term. So the Splash Brothers, so for each of the Splash Brothers, game by game, and for the Warriors, quarter by quarter, we calculated T2 for the observed string hits and of misses, Then we computed the histogram of T2 for the null hypothesis, which is just all strings of the same length with the same fraction of hits. And in small cases, you can do enumeration. In larger cases, you can do random sampling. And then finally, we calculate the empirical p-value of the observed string. That's the experiment. So under the null hypothesis, that there's no hot hand, you'd think that these p-values are kind of uniformly distributed on the unit interval. Absolutely no effect. And so that would make the conditional distribution function look like a 45-degree line. So we want to look at not just one experiment, but we looked at all the games in the regular season and in the playoff. These guys are box plots, so I'm assuming that everybody here knows what a box plot is, but just in case, I'll tell you anyway. This is the range of p-values here for Mr. Curry. The line is the median value. This is the 25th percentile, 75th percentile, the max and the min. So these, a hot hand would have very concentrated p-values down close to 0, representing statistical significance. Curry doesn't have the hot hand by this picture. Thompson doesn't, and neither does the team. And here are the cumulative distribution functions lying very close to the 45-degree line, which is no effect at all. So you can ask yourself, if you do watch basketball, I'm pretty sure you'll see what I see, which is these guys going hot and cold. But whatever it is, and even after accounting for this small sample effect that was neglected by the original study and making it easier to find a hot hand, we didn't find one. So I'm showing you today one experiment. As usual, we've done it about a million different ways, changed the framing and changed all sorts of stuff. We get more or less the same answer. But here is just a little bit more color. The depth of the conditioning set is the number of shots we counted before we looked at what came after. So we looked at 1, 2, and 3. I've been focusing on 2 up until now. And it didn't seem to matter very much. You get kind of like 5% of them, maybe a little more or a little less at the 5% level, just as you would expect if there were kind of nothing going on at all, pretty much independently of this condition that we looked at. It's just a little robustness check, but it was the same story no matter what we did. So one more point, which is that of all the players on the Warriors, I think Klay Thompson is perceived as the streakiest. And in December last year, he did something amazing, which was score 60 points in one game. So a typical basketball game, he has 100 points overall for the whole team, or the Warriors were high this year, so it's more like 110 or 120 sometimes for them. But definitely this guy got more than half the points of the team in that particular game. It was December 6th. It was the poor LA Clippers who got decimated in this game. And here is the string of the 44 shots that Klay took. He made a lot of them. And you would think that if ever there was a moment when the streakiest player had a hot hand, it would be in this amazing game. It sure did look like he couldn't miss. And here is the histogram. That's the null hypothesis, the green and red. Here's the hot hand critical region. And here is the hot hand statistic for Klay Thompson's string for that particular game. Like nowhere near hot. It was almost kind of cool if you believe in that framing of the concept. So there it is. It is a bimodal distribution. We've looked at, just to get a little color of why that might be a bimodal distribution. There are lots of reasons. But one of them is that my test statistic is itself a difference of two test statistics. One of them is the probability of a hit following hit. The other one is a probability of a hit following misses. So you're kind of taking a difference. Of course, it doesn't just difference the histogram, but makes for a complicated looking null hypothesis. And to look at the individual histograms for the first term, probability of the continuation one and the reversal one, The continuation one is in blue. The reversal is in red. The shape of this reversal one is so bad because Thompson made most of his shots. So when you're making a higher fraction of your shots, the histogram, all else equal, starts to look worse. So it's interesting to take these things apart and see. I mean, you can go down and down in an analysis like this and start to see more and more of what the pieces look like. But it amazed me throughout how much there was to study in this extremely simple setting, how it was possible for somebody like Amos Tversky to make a mistake of this kind, for it to stand for 30 years in a very, very well-trodden literature, and then for it to be accessible, easy to do better once you have data science in your hands to work with. So those are the main themes. So just to say what we did here, we ran a version of the hot hand experiment that was in Gilovich and in Vallone and Tversky, done in 1985. They did the Philadelphia 76ers and the Boston Celtics, and varsity and junior varsity teams, men and women, by the way, at Cornell. We ran their experiment, more or less, on the regular season and in playoff games for the Golden State Warriors. We examined shooting records of Steph Curry and Klay Thompson, game by game, and also streaks for the team, quarter by quarter. Our version of the experiment didn't use any asymptotics. We just relied on being able to bootstrap or do permutation tests, or in some cases enumerate an entire null hypothesis with a computer. And when you do that, you automatically take account of the small sample bias in this paper by Josh Miller and Adam Sanjurjo. So the evidence from this experiment supports the original findings. So it's kind of like an odyssey, right? We ended up a little bit where we started, although it was eye-opening for me to do this. And we came to the same conclusion, even though what we effectively did was make it easier to reject the null hypothesis. We were still unable to do that. And this is certainly not the end of the hot hand study. I don't think they're taking down that hamburger sign or anything. A question, if you're interested in psychology, that you could ask is, what the heck is it that people are seeing when they think they're seeing a hot hand? It's not the thing we measured. It's just no sign of it in that measurement. We've tried lots of variants, including ones that are just counting streaks and just looking at hits and ignoring conditional probabilities and looking at kind of excess tails. We can't find anything so far. All I can say is that this really contributes to the growing body of evidence that the way humans perceive randomness is not perfect, is highly imperfect. So there's that literature, which to the best of my knowledge is really launched by Kahneman and Tversky, is growing. So one of the, just to finish up, one of the earliest papers by Kahneman and Tversky is called, it's called Belief in the Law of Small Numbers. So everybody knows the law of large numbers. They were kidding, right? They said people look at small samples and draw all sorts of conclusions from that they should not be drawing. This is one of the papers that put them on the map, and they have this quotation: "The true believer in the law of small numbers commits his multitude of sins against the logic of statistical inference in good faith." We see that Mr. Tversky wrote a paper about this very subject in 1971, and then went on in the next decade to make his exact own mistake. And I like to think, if he were here with us today, he would be very pleased to see all the developments around that. Here are the Splash Brothers. And one more thing. So there's another star player that we didn't focus on, Kevin Durant, who is credited more than any other player with dominating the playoffs. He's quite amazing. We didn't change the title for him, although we did run all the statistics on Kevin. In fact, when we had this, some blog posts out about this during the playoffs, and the comments, we got lots of comments, and people would often write, you know, Lisa, you're looking in the wrong place. It's Kevin Durant with the hot hand. But actually, he doesn't have a hot hand either. This is his statistics, you know, right around 5% at the 5% level. He played fewer games because he was injured in the spring. But KD, that's KD. So that is almost the end of my slides. That's Vallone, and that's Nishant, and that's me. And thank you.